On this board we will see 3 theorems, all of them showing how to use non-determinism, NFAs, to prove the 3 closure operations. For example, that the class or the set of regular languages are closed under the 3 operations of regular operations of union, concatenation, and star. So we will show those regular languages are closed under those 3 operations, and we will prove that that's the case, closure, using NFAs, using non-determinism as the tool to make the proof. Okay? Now that'll take up, let's see, 3 or bit over 3 of the sessions, of the 4 on this board, and then towards the end, in the 4th session, we'll start a whole new section. So it'll be 1.3. So it'll be the 3rd major section of the chapter. Let's see how many sections there are in chapter. It's chapter 1. There wouldn't be very many. Well, there's only 4 total, and the 3rd one that we'll start on in the 4th session is called regular expressions, and the next section, several boards away I guess, 1.4 is called non-regular languages. Now that sounds interesting because a regular language, remember, by definition, is a language that's recognized by some finite automaton. A deterministic, a DFA, or an NFA. And remember, a DFA is equivalent to an NFA. So a non-regular language, I guess, means that it cannot be recognized by such a finite automaton. But in other words, there are languages that DFAs, NFAs cannot detect, and that's interesting. Okay, so we'll start on the 3 theorems. We will use the NFA. We'll use NFAs. Of these 3 proofs, the first 2 involve 2 NFAs, and the 3rd one involving the closure of star operation. Star, remember, operates on 1 language, so we only need 1 NFA in that proof. So for the first 2 we need 2 NFAs, and the 3rd one we need 1 NFA. Okay, so let's we'll start with there are 3 operations, right? 3 regular operations. So union, concatenation, and star. So we'll start now on the proof of the first one, union. Now we've already done it not using an NFA, not using non-determinism. We used determinism, and we took our kind of like our memory in the DFA had we used a Cartesian product type trick to get the proof. Now, so we're going back to that application, trying to prove the closure under union, the closure of regular languages under the operation of union. And closure just meaning, of course, that the result that you get also belongs to the set. Maybe a bit of revision here might be useful. The very concept of closure, remember, speaking generally, you have a set called S, you have some operation called P that operates on the members of that set. It might operate on 1 member, or it might operate on 2, depends if it's a unary or binary operation. Okay, so you apply that operator P on members of the set S, and if the result that you get, after applying the operation on the members of the set, if the result also belongs to the set, then for any members of the set that you operate on, or for all of them, then by definition that set is said to be closed. under that operation. Now, if you've done any group theory, closure is basic. It's like one of the fundamental postulates that the elements of a set have to obey to be a group. You know, a group's just a special kind of set. Okay, so closure, very important concept. Right. So we are now doing the proof of trying to show, to prove that the class or the set of regular languages is closed under the operation of union. That's a binary operator. It takes two languages, unions them, in other words, combines all the strings of both languages to make a much bigger language, usually, and that result is also a regular language. In other words, it can be recognized by some finite automaton, right? A DFA or NFA. Alright? So that's what we have to prove. Alright? So go back to, say, page 45. Have a look at the old proof we had, using the Cartesian product. And then once we've done this one using NFAs, non-deterministic finite automata, ask yourself which of the two approaches is sort of easier. And that's one of the major points of these three proofs, is the NFA, the non-deterministic approach, is easier. Now, before, when we were trying to prove closure with concatenation, we got stuck. We just didn't know how to proceed. So we just sort of put things on the back burner, so to speak, waited till we had discussed and learnt about NFAs, non-deterministic finite automata, non-deterministic computation. And now we have those tools, now we can actually use them and complete that second proof, and we'll go on then to use NFAs to do the third proof on star. Okay, and then after that we'll start talking about regular expressions. And we talked about so far regular languages. They are any regular language has an automaton, finite automaton that recognizes it. Finite operations, like the three we're talking about, on this board. Union, concatenation, and star. And then we'll talk about regular expressions, define what that means, and show in later boards what you can do with them. Very powerful technique. Alright, okay, so theorem 1.45, as usual, 45 is the 45th thing in the chapter that gets labelled numerically. A thing might be a theorem, might be a corollary, might be an example, it might be what else? Definition, and so on. Okay, so the 45th thing. So as I keep saying, but it's useful to know that Sipser uses what I call global ordering. So when you have to look back in the text to find something, and say it's 1.25, let's say, and you flip the pages back and you come to 1.27 and say, oh, it must be close, and just go back to find 1.25. Whereas if Sipser or any author does not use global ordering, finding the thing that you're looking for can be confusing and difficult, because all these numbers get all mixed up. Like if you're numbering in order the theorems, like the theorem 22, theorem 23, theorem 24, which may be inserted in those may be like definition 42, or so all the numbers just no longer in order, and it's very confusing trying to find something often. So global ordering is useful. Okay, so I suggest you do it if ever you come to write mathematics textbooks. Okay, as usual, Sipser, theorem statement, proof idea, and then the detailed proof. And in practice, noticing that the heart of the proof is actually in the proof idea, and so a lot of the actual proof assumes important knowledge